Here's how to become the best Python developer in your company in under 60 days. Our thesis is that you can increase your speed, quality, and effectiveness of software development by a factor of 10 or more. This happens when you learn the first principles of Python and how to apply them in software engineering best practices. The outcome is that you are able to write valuable software tools that no one else around you can create. You become known as the person who solves problems no one else can solve. This does have some social downsides. Your coworkers may become jealous or feel threatened by you. Interviews become awkward as it becomes clear you're more knowledgeable than the interviewer. Performance reviews can be disrupted for similar reasons, but most people find the upsides are worth it. The key to accomplishing this quickly is efficiency of deep, focused learning. You make certain choices and follow a learning path different from others who get slower results. The exact steps are explained in this presentation. My name is Aaron Maxwell. I'm a software engineer and an author. I have worked in several Silicon Valley engineering teams, including 2 unicorns, SnapLogic and Lyft. After working full-time as a software engineer for a decade, I partnered with O'Reilly Media and created an extensive advanced Python curriculum. This was designed for working technology professionals, not for people new to coding or new to Python. Over the course of 2 years, I taught this curriculum in repeated live sessions to over 10,000 professionals worldwide in almost every engineering domain, country, and culture. I also wrote a book called Powerful Python, with a new edition published by O'Reilly Media. Books are valuable for learning, but we all know there's a gap between reading information and gaining new capabilities, which permanently transform your day-to-day work. For this reason, I also created a professional training program called Powerful Python Bootcamp. Powerful Python Bootcamp is different from other bootcamps because it's made for established technology professionals who already write Python in their work and who want to rapidly level up their Python and software engineering skills to world-class levels. Our methodology consistently produces these results in 60 days or less, with only 5 to 10 hours per week. How can you do this on your own? Here's a high-level process. First, you focus on first principles. This produces the greatest boost to your abilities from your investment of deep learning time. Next, you choose learning topics in Pareto optimal order. We'll explain what this means later. Then you apply this in a project, which you use as a focus for professional self-promotion. And you do all this in a group of ambitious peers, for accountability and for better learning. Let's dive into each of these. Every domain of human activity has its own first principles. These are the foundational concepts, distinctions, ideas, and mental models upon which that domain is based, and which generate all value and results. Some examples of the first principles of software engineering include design patterns, mental models like complexity analysis or Big O notation, and best practice guidelines such as the solid principles. And there are 2 facets of first principles you want to understand. The first is the general skill of reasoning in first principles. This universally applies to all domains. It doesn't matter what you're doing. And the other facet is knowledge of the relevant first principles for a given specific domain. In particular, we're focused on programming, because here's the big benefit. When you learn how to think in terms of first principles, and you gain knowledge of the first principles for a particular domain, you suddenly become capable of great achievements. You can do things you never could before, and which sets you apart from everyone else in that domain. You find yourself getting creative insights quickly and repeatedly. You routinely solve seemingly intractable problems. You regularly produce surprising new inventions. Because when you get down to it, all innovation comes from combining first principles in novel ways, from discovering new first principles, or both in combination. For software development in particular, mastery of first principles produces a quantum leap improvement in your coding skills. And we want to make an important distinction. Understand the difference between language-independent first principles of software development and the first principles of the programming language you use. You need both of these. Let's look at each of these separately. The first principles of software development are universal and timeless. They are independent of programming language and will be valuable to you for the rest of your career. It is critical to master these, because doing so grants you the ability to create unusually powerful software solutions which others cannot, and which you could not create in the past. In addition to this, Each programming language has its own first principles. These relate to the semantics of that language, to the features it uniquely provides, and how they enable you to rapidly express solutions. Mastering the first principles of Python amplifies your speed and quality of development when writing Python code specifically. The strategy design pattern is a first principle of software development. It lets you select an algorithm at runtime as a parameter to another algorithm. Again, this is independent of programming language. Let's look at one of the first principles of Python itself, called the function object abstraction. And the way these relate is that in Python, you can use function objects to easily implement the strategy design pattern. This is demonstrated by key functions for Python's sorted built-in. Here we have a list of positive and negative numbers. If we pass that list to sorted, we get a new list of numbers in ascending order. But we can also call sorted with a key parameter, and its value will be a function object. In this case, we're passing in abs, ABS. That's Python's built-in function that gives you the absolute value of a number. And we pass that in as the key for sorted, then we get different behavior. We get the numbers back in order of increasing magnitude, in order of their absolute value. Your focus on first principles is how you access your creative genius. When you learn how to reason and operate from first principles, and you learn to apply that to a specific domain, you become a creative genius in that domain. Because suddenly you're able to make connections and insights that others cannot. Your abilities become recognized as rare and valuable, and your level of mastery allows you to contribute more than anyone else on the team. An important foundation for this is object-oriented programming. Most people know that OOP helps you organize your code, but very few people understand that OOP also organizes how you think about your code. And this is extremely important. This has roots in cognitive psychology. Like all humans, your reasoning is denominated in the abstractions you create. That means you can improve the results of your reasoning by using better abstractions. Does that make sense? This is related to the well-known 7 ± 2 rule, which was created by Harvard psychologist George A. Miller. Dr. Miller's publication on this concept has become one of the most widely cited papers in the history of psychology, which is why the 7 ± 2 rule has come to be known as Miller's Law. The idea is that human minds optimally reason in terms of a small number of chunks. Yes, that's a formal term in psychology for the unit of information that you hold in your mind, chunk. And it turns out that optimal number happens to be close to 7 in most people, hence the name of the rule. And there's an obvious way that this applies to programming. If you have a small set of classes, which map well to the business logic of what your program is attempting to do, it becomes exponentially easier to reason about your code base and accomplish what is needed. In contrast to if your classes do not map well to the business logic. Is this making sense? How does this relate to exceptional coders? Because there are programmers that are just far better than average. And the 7 ± 2 rule applies to them, just like it does to you. The difference is that they've learned to make more powerful distinctions and abstractions. That matters because classes represent abstractions we can reason about. When you choose the right abstractions and design classes which represent those abstractions well, then your thinking is ordered in the most empowering mental model for solving the problem at hand. And this changes how you write your code. You find you can write high-quality software faster. Your odds of successfully solving the problem you want to solve go way up. Your code seems more elegant and clear, and it omits anything not necessary. It's more elegant, uncluttered with cruft. A good example of this is the DataFrame class. You may know about this. It's from the library called Pandas. And it's an abstraction, a Python class, which has changed the world. Understand these abstractions are created. Once upon a time, there was no such thing as a data frame. It was made up. Someone created it. And when they did, it empowered countless coders to perform remarkable feats of data processing with far less effort than ever before. We could say similar things about Python's built-in data types like dict and list. And this also applies to other widely used classes. All this means that you can create your own abstractions, your own classes, which will unlock massive productivity for you, your team, and possibly the world. Let's dive into an example. It's a class called DateInterval. This class represents an interval or range of days. It has a start date and an end date, and it allows you to succinctly express operations on that interval. See here how you create it. You pass two date objects to its constructor, the start and end date. So what can you do with a date interval? You can check whether a particular day is in the interval or not. See here we have two date objects we've created. One is in the interval, one is not. And we use Python's binary in operator, in, to check. That gives us a yes, no, true, false answer to the question of whether a particular date is in the interval. You can ask how many days are in the interval using Python's built-in len function. You can even use a date interval instance in a for loop, going through each day in sequence. Step back and think about how this changes your thinking about your code. The date interval class is the Python code manifestation of an idea. You are now thinking in terms of a date interval when you write code using instances of this class. If there was no date interval class, you would not easily be able to think in terms of a date interval. Your chunks would be more complex and disconnected. Here's the source code of the date interval class. It's not important to understand everything here. You can screenshot this and step through it later if you like. But just notice it's using some sophisticated Python features, working together in a fluent way. And if you don't understand all those Python features yet, that's fine. That's not the point here. What matters is that you understand that you're creating a new abstraction called a date interval, and this new abstraction empowers you to more efficiently reason about your code base. Of course, it also makes it easier to write good code and to write it faster. On top of this, there are the more classical benefits of object-oriented programming, like code reuse, encapsulation, data hiding, and more. But even these factors relate to how we think about our code. The next pillar is automated testing. If OOP is the foundation, writing tests is the supercharger. When you apply the patterns and best practices of writing unit tests, integration tests, and other test forms, you find this tremendously boosts your capability to create sophisticated, powerful software systems, especially for complex software. Automated testing does not help you that much when you're writing small scripts. But that's not why we're here. There's just not that much value in learning how to write small scripts better. Your greatest contributions come from creating complex software systems that solve hard problems people care about. This is where automated testing becomes a superpower. In particular, automated testing will tremendously boost your development speed. Again, not for small programs, but that is not why you are here. Automated tests enable you to successfully create advanced software systems you simply could not before. The full power of automated testing depends on object-oriented programming. You can create simple tests without classes, but the most valuable testing patterns require full use of Python's object system, and that is why OOP comes first in Pareto optimal learning. One reason automated testing is so valuable, it effectively reduces the complexity of the program you're implementing. This makes it easier to implement mid-sized programs, but the real value is that it enables you to create extremely complex software that would otherwise be out of reach. Automated tests raise the ceiling of complexity you can successfully handle by a wide margin. Let's look at an example. Imagine you're creating a web application framework. You want to have view objects, which represent the HTTP response, and you need a way to map incoming URLs to those views. You're going to create specialized view classes for different response types and a class called WebApp to coordinate this configuration. Here's a way that might look. You create an instance of this WebApp class, and it has a method called addRoute, which you call with two arguments, the incoming URL and an instance of the correct view class. Here's one way that might look. You create an instance of the WebApp class, and it has a method called addRoute, which you call with two arguments, the URL that triggers that response, and an instance of the correct view class. Your WebApp class also has a get method, takes a URL, and it returns the HTTP response that goes back to the client. Now, there is enough complexity in this web app framework that if you just started coding it, odds are there will be bugs that you will miss by manual testing. Even worse, at this threshold of complexity, every new feature you add will risk breaking something in some unexpected way. The only way to maintain full correctness is to exhaustively test after each change. But to do this manually is extremely labor intensive. The solution is to start by writing a suite of automated tests exercising the key functionality. For the web app class, that may look like this. Again, it's not important to understand all the details here. What you have here is a test case that exercises the web app class and its behavior in different circumstances, calling methods and checking the return values. Here's the fun part. Once your tests are implemented, writing the application is straightforward. You just write code to make your tests pass. And when that is done, you feel full confidence that your program is working correctly. This is especially valuable when implementing complex functions and classes with intricate edge cases. Just for the record, here's how you might implement this web app framework to make these unit tests pass. Again, the details don't matter. You can screenshot this and study it later if you like, but we have a web app class with an add route method, a get method, and a method called URLs that returns a list of strings. We also have an abstract view class with a render method that returns a string, and we have concrete subclasses of this base view class, like this HTML view class, which takes a file name to define the content of its response, and a JSON view class, which takes a JSON object in its constructor and returns that represented as a string. The details are less important than understanding the pattern. First, you fully specify the desired behavior of the complex system by writing automated tests. Then you rely on those tests to provide thorough feedback as you implement the code. And you run these tests frequently as you continue development. Because it costs you no effort to do that, and it immediately exposes any bugs you create while you're adding new features and reorganizing your code base. And you continue to benefit from the test suite over time as you refactor the code base, add significant new features, and make other disruptive changes which threaten to break your program in unexpected ways. In the end, you have created a rich and powerful program with low stress, high confidence in its continued correctness, and little effort spent on tedious manual testing. This is why we say automated testing is a superpower. It simply puts you in a different tier of technology professional. Next, we come to data scalability. When processing large amounts of data, some programs are responsive, efficient, and rock-solid reliable. And some are not. They will hog machine resources, randomly hang without warning, or even crash when you push too much data through them. The difference comes down to space complexity. This is the area of algorithm analysis that is focused on effective usage of memory by programs. When designing an algorithm to process a large quantity of data, how can you make it use as little memory as possible, and with a reasonable upper bound that is independent of input size? This is important due to how operating systems manage running programs. Imagine your Python program is creating a large list of dictionaries, or instances of some other class. When a program creates a large data structure, it must request a block of virtual memory from the operating system. But remember, the operating system must allocate resources to all programs. The job of the operating system is to allow all programs to run, and to prevent any one program from starving the others of enough resources to run. So the OS will not always give your program the full amount of memory you ask it for. If a program asks for too much memory, the operating system will do something called paging to disk. This means that the OS will give your program a block of pseudo-memory. This pseudo-memory is written to and read from the persistent storage layer, like the hard disk or solid-state drive, instead of actual memory. This affects performance. In fact, this shoves your performance off of a cliff. The sluggish I/O speeds of disk compared to memory reduce raw performance tremendously, typically between 75 and even up to 90%. This can literally make your program 10 times slower. This also has an impact on user experience. If a human is interacting with your program directly, they will experience it to freeze and seem like it's stuck. In extreme cases, and to ensure that other programs have the resources they need, the operating system may even kill your process completely. This is why memory-efficient algorithms are important. Those who are skilled at writing big data programs learn to code in memory-efficient ways, keeping the process within a reasonable memory footprint regardless of total data input size. This is an essential skill for top performers who work in technology, because big data is here to stay for all of us, for everyone. Software processing more data than fits into memory is increasingly the norm, not the exception. So how do you accomplish this in Python? The key is a feature called generators. Many Python users have heard of this. You've probably seen the yield keyword yourself, but most people do not know the depth of this rich feature of Python. This includes the coroutine model of generator functions and its implications for algorithm design, generator design patterns, like fanning record streams in and out, and the scalable composability strategy for implementing robust and flexible internal data processing pipelines. So how does this relate to first principles? At the software engineering layer, you have memory-efficient algorithms which are independent of language. And at the Python language level, you have Python's memory model, along with its generator feature. The language level first principles form a bridge to the higher level language-independent first principles. You need both. Let's look at an example. Here's a function called matching lines from file. It reads lines from a text file, choosing those which contain a certain substring, and it returns a list of strings, the matching lines. Notice it creates a new data structure, the list, whose size scales up in direct proportion to the size of the input. How does this affect the memory footprint of the process? If the text file is small, or if only a few lines in the file match a pattern, then the resulting list will be small. But if the text file is large with many matching lines, then the memory allocated for this list becomes substantial. It is very easy for this to cross the threshold where it must be paged to disk, plummeting the performance of the entire program. So let's look at another approach. Here's matching lines from file, but implemented quite differently. See the yield keyword on the last line. This makes it a generator function. Now, we won't go into the details here of what this does to transform the algorithm completely. The bottom line is that instead of returning a list of all matching lines, it now produces those matching lines one at a time, as they are encountered. For functions like matching lines from file, you typically use them in a for loop, where you only process one element at a time anyway. This means your memory footprint is now the size of the longest line in the file, rather than the total size of all matching lines. The result is that this small memory footprint holds no matter how large of an input file you feed it. Suddenly, your algorithm is exponentially more memory efficient, with none of the problems plaguing the first version. The best approach is to proactively infuse all your Python code with memory-efficient generator functions, as a standard practice when developing. This naturally makes your programs perform their best, regardless of hidden memory bottlenecks that you missed, and regardless of unexpectedly large input sizes. The next big topic to understand is called metaprogramming. You see, most Python code operates on data, but it turns out you can also write Python code that operates on other Python code. This is called metaprogramming, and it is one of the highest leverage things you can do when creating software. Coders who use metaprogramming are able to rapidly create tools and components that other developers simply cannot. It is like the difference between riding a bicycle and flying a jet. You not only travel faster, you can go places you simply could not reach at all with a lesser vehicle. There is a reason that the world's best software extensively uses metaprogramming. You can find examples of metaprogramming in the source code of the most successful Python libraries. And there is a reason that these extremely powerful software tools heavily use metaprogramming. Let's look at an example to illustrate this. Imagine this function, which makes an HTTP request to an API endpoint. It's very simple. When you call this function getItems, it has just one line calling request.get with the URL. And then it returns an object representing the response from the remote server. Suppose the remote API has an intermittent bug. so that most of the time it works great. But it turns out that 1% of requests will fail with a status code of 500. This is the HTTP status code that indicates an uncaught exception or some similar error on the remote server. And you cannot really make the API team change it right away. You can ask them to fix it, and maybe they'll eventually get around to it. In the meantime, you just have to deal with it. So what do? Here's the key. You realize that if you make the same request again, it has a 99% chance of succeeding. So you modify your getItems function to retry up to 3 times. This reduces the failure rate from 1 in 100 down to 1 in 1 million. Here's what the code looks like. We're not going to go into this in detail. You can screenshot this and study the code later if you're interested. Just know that this will detect when the remote server returns a status code of 500, and if it does, it will retry the request up to the maximum number of tries. So this is great. This effectively solves the problem because it reduces the failure rate down to an acceptably low level. Now imagine you need to do this more than once. Imagine your application does not have just this one function that's affected by this issue. Imagine it has many functions which make requests to different endpoints of this API, all of which have the same problem. How can you capture the retry code in an easily reusable way? The best way to do this in Python is with a metaprogramming tool called a decorator. The code for it looks like this. Again, we're not going to go through this function and explain how it works. Take a screenshot if you want to study it later. But what it does is generalize the retry algorithm that we had previously integrated inside the getItems function. It extracts that algorithm and encapsulates it in a form that we can easily reuse with other functions and methods. You do this with a special syntax in Python using the @ character. This is what it looks like. We use the original version of getItems, the one-line naive version, but notice on the line just prior to the def, we say @retry. And the great thing is we can apply this to any other function or method. If we have different callables for different endpoints, we can easily apply the same pattern to all of them. Even better, this retry logic is fully encapsulated in the retry function. You can change the number of retries, implement exponential backoff, or make any other changes you want all in one place. All decorated functions immediately reflect your updates. There's something else going on here: ease of reuse. Metaprogramming often allows you to implement solutions to extremely complex and difficult problems in a way that people can easily reuse. This retry function and the decorator that it implements, it's really rather advanced code. Not every Python developer will be able to write code like this, but you used it to solve a problem facing the entire team, and you packaged it in this tool that is instantly usable by everyone. Not only does this boost your contribution to the team, it also affects your status in the workplace. Your presence on the team has amplified everyone's productivity and systematically improved the reliability of the entire application in a way that everyone recognizes right away. And this leads into the next phase of your mastery, what I call synthesis. Much of your learning is going to be bottom up, meaning that you are studying specific topics in depth with a period of intentional focus. And we do this because it is efficient. You're portioning each learning curve down to a reasonable size so that you can solidly master that one topic, then build on it as you move on to the next. But here's the thing. That is not how you create real software, is it? In a real program, you constantly use all features of Python, all mixed together all the time. It is smart to learn the building blocks first, but you must also learn how to compose them together. In Powerful Python Bootcamp, students learn synthesis in 2 ways: through the study of real-world production code bases and through guided construction of software projects from scratch. There's another factor here. Real software is often made under deadline pressure with competing priorities. As a result of this, real software is never perfect. It could be perfect if you invested the time and energy at the expense of other important tasks. But that's not what you do. because in practice, you have many priorities competing with each other. All of them are important, and all of them have their own aggressive deadlines. The way that skilled programmers manage this is by writing code which meets the requirements to a good enough standard of quality. At that point, instead of devoting additional hours to refining it, you move on to one of your other tasks that were due yesterday. How do you navigate this? How do you reckon this good enough threshold? How do you make these decisions, these judgment calls, when you have so many competing and sometimes conflicting priorities? This is an important key for thriving as a technology professional. At some point, you will probably want to develop an open source project. So when you create an open source project, how do you choose what to build? Some people choose a project based on what they think will be fun for them to create. Other people will choose based on the technology that they will learn through creating that project. But in Powerful Python Bootcamp, we use a different criteria altogether. We call this your artifact. Your artifact is an open source project that you create. Your artifact is a marketing asset. Its purpose is to market you. Your artifact is a dynamic marketing asset which efficiently signals your elite status to the job market and attracts the opportunities you want. Every word of this matters, so let's break it down. Your artifact is an asset. That means it is something you create which generates more of what you want as a side effect of its existence. It is a marketing asset. Its purpose is to market you. It is a tool for professional self-promotion. It is dynamic. As technology and the world evolves, you refine your artifact to adapt to new job market conditions. Your artifact signals your value. It demonstrates your expertise, communicates your skills, and broadcasts your value to the job market. As your goals change and as you learn to think bigger for yourself, you pivot the artifact to signal differently. It does this signaling efficiently. What your artifact communicates about you is communicated immediately. It is instantly believed by default with little or no skepticism. Just like the author of a book is assumed to be an expert in that book's topic, in the same way, your artifact creates instant and powerful first impressions of you. Your artifact signals status, your professional status, your industry reputation, and the esteem in which others at the top of your profession perceive you. It attracts the job opportunities, the professional relationships, and ultimately the career you're looking for. Your artifact can take several forms. It can be a software tool which is used by your peers to do their work. It can be a software library used by your peers when they write code. It can be a web application useful to people in your domain of technology. It can also be a book, though that's much harder, and I speak from experience, so I recommend you do one of the above first. Understand something extremely important. Creating your artifact does not need to be difficult. It does not have to require a lot of work. The notion that success can only come from extreme exertion, that is a limiting belief. The career-boosting results of your artifact are largely independent of the effort and time that you put into it. In addition, understand that your artifact does not need to become famous in order to help you. None of my artifacts were ever famous, and it also does not need to be something that many people know about, like Pandas or Nginx or Docker. That is not in any way necessary. What you want to do is to create an artifact which is famous among the right people in your domain of technology, those who can help you attain your goals. And if other people do not know about it, then who cares? The mere existence of your artifact has a shocking effect. It makes people assume you are in the top tier immediately and uncritically. And it does this very efficiently in terms of your time and energy. This is a status hack. Like I mentioned, you can also create this effect by writing a book. But speaking as someone who has done that several times, writing a book takes massive amounts of time, typically years. In contrast, you can often create the initial version of an artifact in one weekend. Just that can be enough to start influencing peers and strangers to see you in a completely different light. Creating the right artifact will change how you are perceived by your entire peer group. It does so more efficiently, immediately, and usefully than any other method. It just requires the right strategy. Now, besides building your technical skills and creating your artifact, the most important thing you can do for your career is build your network. I'm talking about the human network, not the computer kind. And while there is certainly a personal aspect to networking, the fastest way to build your network is by creating content. Now, how do you do this in an easy, low-effort way? Well, it turns out the easiest way to create content is by writing LinkedIn posts about your artifact while you're building your artifact. And this has many positive effects. First, it communicates your artifact publicly. This builds awareness of your artifact over time. And you are leveraging the social media algorithm when you do this. LinkedIn's algorithm will notice who engages with your posts and then show it to similar folks, automatically extending your audience. You will naturally attract attention and professional connections from the right people. The mindset you want to have is that content creation is networking. It is an easy, exceedingly time efficient, and tremendously high impact form of networking. And it is powered by your technical skill base and by your artifact. You want to do this in a group. Doing all of this is hard. It is almost impossible to accomplish on your own. There's a real risk you will just not succeed. What helps tremendously is to do it with others together in a group. And doing this with the right people increases your odds of success and the speed and ease of your progress. Everyone knows that you are the average of the people closest to you. So who is in your group? That matters. Pairing with the wrong people is worse than trying to do it on your own. They will drag you down and prevent you from succeeding.